So basically, we're gonna like start by. So this basic course is gonna this lecture is gonna cover matrix calculus, just the algebra, so that people are more comfortable with it, and so that when it gets used in more difficult settings, like when Raman uses it in derivations, it's more easy to follow along. So that's what I'm gonna focus on first, and then if there is still time, we will sort of go over the proof that Raman did, or SPD and some of the theorems that he used. But basically, stick to the math or the algebra and how it applies and where it applies.
Just a second before you start. I mean, I can see the seconds ticking, so I guess it's working. It's recording right now, right?
Alright.
I mean, I've never used it earlier, so I hope it's working.
Yeah, I guess it must be. So yeah, okay. So if some of the material seems obvious, then bear with me. It will get interesting. So yeah. So first of all, I'll try to motivate why do you even want to take a derivative of this equation, or in what situation this arises. So what kind of functions or what kind of physical functions you would actually encounter that would require such a technique, or you will have to take a derivative. So one equation is this. But why would you have to take a derivative of this, in a physical scenario? Any suggestions? Any place where you have worked, where you had to take such a derivative, in your projects?
I don't know, probably when you have to define maximum, when you want to find optimal value.
Right. So, but this is a, let's say, this is a linear system, right? It would, things will just keep on increasing as you take a derivative. You won't really reach a maxima or minima in this particular equation. But let's say, if someone was doing some kind of a modeling where the system is a linear model. So I did electrical engineering before coming here. So you have a PID controller, some control, or you have robotics. You're modeling the motion of the robot as a linear system of the inputs, and you want to know how far the arm will reach when you apply more electricity, I guess, when you put more input into it. So that's one thing. Another thing, the one that I've laid out, which I think is more interesting and actually sort of even gives the intuition of why vector spaces are defined with inner products the way they are, why they are defined as cosine angles instead of actual distances between vectors, is if you want to model how the magnitude of this vector changes as you change the magnitude of this vector, or if you change this vector itself, x, how would the magnitude of this thing change? So we know that magnitude and norm, I'll be using it interchangeably. So the magnitude of this is basically given by y into y transpose, or y transpose into y. So by the previous slide, we can see that y is equal to ax. So y transpose into y is going to be x transpose a transpose ax, right? So basically, this equation or this function is giving me the magnitude of the vector y, my output. So now, what you can see here is that this has a very special form. This matrix you can write as M, so I will always denote M as being this matrix. But this matrix, by virtue of coming from here, has certain properties. As in, I have formed a matrix by multiplying a matrice's transpose to itself. And that gives rise to the properties of positive definiteness or semi-positive definiteness, symmetry, and all those things. So we constantly, Raman will constantly keep talking about how when things are symmetric, there are certain properties which hold. How when things are positive definite, there are certain properties. There are certain properties which hold. Now, the reason, one of the more intuitive reasons for that is when you are, say, modeling the magnitude of something, these kind of forms really arise naturally. And so at this point, like, I'll take a detour to point out some important facts which are here. So this thing is also called a quadratic form. So that's just a name, but it's basically a matrix M is called positive definite or strictly positive definite if for all x this quadratic form, this function remains greater than 0. And there are lots of different ways to characterize them. So A is strictly positive if and only if, so it is always Hermitian. Hermitian means A equals to A transpose conjugate, A conjugate transpose. So, and one of these things holds, like if any of these, if it is Hermitian and the first is true, then all of these things hold. So you will see that in my case, like in the previous example, where M is equal to A transpose A, I think the third one will probably apply. Yeah, the third one will apply. So there exists a B such that, oh yeah, so some notation first. There exists, and then exclamation means there exists a unique. There exists a unique matrix which will have that property. This is just simple, there exists. And the 2 colons means such that. So there exists B such that. So A equals to B conjugate transpose into B, and determinant of B is greater than or equal to 0. So this property, if I make it so that this property is holding in the previous system, if A is such that its determinant is greater than 0, if it is non-singular, therefore when I try to find the magnitude of the output using this quadratic form, this M matrix is going to be positive, strictly positive definite. And so non-singularity and positive definiteness are entangled, or they come together, and symmetry, they all come together in very naturally in linear systems and linear equations. And that is why, like, and they have like, so they have nice properties. When you study them mathematically, like, you forget about the systems themselves and just focus on the mathematical structure, and you start with the properties like the axioms, and then derive theorems from it. So there are lots of these, so there are 6 of these which I've written, and I copied them all like from the first page of this book, positive definite matrices. So, okay. So now, like, back to the original question. So the original question was that you want to find out, like, how does the magnitude of this vector changes as you change this vector x. So what we did was we actually wrote down the magnitude of this vector, x transpose, a transpose, so y transpose into y, which is equal to this, and we got this. So this basically is telling you like why you might want to take a derivative. And this here you will see is a quadratic form. This thing is actually going to have a maxima or a minima. Like when you take the derivative, you're going to see that this thing is going to reach a point, like there might be a point where if you constrain the magnitude of this thing to be a certain constant value, you're going to have like these maximas and minimas that you will see in the output, maximum or min. Alright, so okay. So now basically we have to take derivative of some system with respect to x. So like now basically I have just motivated the problem, but let's go back to the original point. So like Samaji suggested that y equal, so we can take, let's say we want to take the derivative of y equal to ax. So I'm now going to go on the board basically. So first of all, can like someone tell me like what is the derivative? Wait. I can go run and get back to get a pen. But yeah, I do need a pen. So I see if I can find it in some other lecture room. But yeah, just think about like if you were to take derivative of this equation, y equal to ax with respect to x, what will be the derivative? How would you define dy by dx to y equal to x? I'm gonna, so you, no, yeah. Okay, so one reasonable thing to do might be to actually collect all the partial derivatives. So if you collect these things, and put them in a matrix format, you'll see that there are two ways to do it. One is if you lay it out in the so-called numerator form. Another is if you lay it out. So this is just a layout convention. Like this is just convention. This is just syntactic thing, which you need to be consistent with. But there are like two choices you will see. So does anyone see the difference between these? Elan, do you see the difference between these?
Between the left and the right?
Yeah.
Just the ordering of the...
Yeah, one is the transpose of the other, right? So this is called the numerator layout. This is the denominator layout. The reason why I'm saying that is because so I'm going to introduce, say, the matrix cookbook, or I'm going to introduce some other people's work. They would have assumed one layout or the other. And depending on the layout you choose, like the formulas, if you try to take from them, like if you just try to use those formulas, you'll have to be careful that they're using the same notation, convention as you are. Otherwise, when you're like trying to solve something, you will make a mistake and take the wrong one, and your answers will be wrong. Like they will come out being gibberish, so you wouldn't make sense. So just make sure that the convention is correct whenever you're using it. But finally, okay, so now everyone knows partial derivatives, right? So what will be this thing? Someone who I haven't asked yet. So what will be this partial derivative?
A11.
All right, yeah. This one, just keep asking, saying that. What will be this partial derivative? I forgot your name. What was your name?
Dave.
Dave, yeah, okay. What will be this partial derivative? Dave. It is
A12.
del y1, yeah, okay, A12. And then next
A21.
alright. And then A22. So this becomes the matrix A itself. So note that the way we have used it, this is just a collection of partial derivatives. It is not the traditional differential. So there's a slight difference between those two things.
This is the Jacobian.
So there's like slight difference, like functionally or like as a collection, they will look the same. But it's just I want to introduce the Jacobian once I am introducing like differentials. So like they are more easily motivated. But yeah, I mean you can think of this as a Jacobian. The only thing is just make sure that the convention is correct, because here if you use this denominator convention, it will be A transpose. And so I have seen, like yesterday I went to the library, I saw like 6 books, like 4 were using numerator, so like, it was very spread, right? And on Wikipedia they actually have the page where they give a layout, numerator, denominator, like formulas converted to each other. So it's like pretty spread. So okay, so we have to find this to be the derivative. So these are the questions that I wanted to just answer to make sure that so one, why is it a matrix form? Because it's just a collection that we have put together in a matrix form, so that there are other formulas, so that we can build upon it. So like this itself is not going to be so interesting. What's going to be interesting are derivatives of x transpose mx, or derivative of this with respect to, so like what is the derivative of the determinant of a matrix with respect to the matrices entries themselves. That might be a question. What will be the determinant of this quadratic form with respect to the entries of the matrix themselves? So like these kind of things are what will be used in the derivations on the slides that of the theory that Raman is going to go through in the class. Okay. So I'm gonna go over like these formulas now, basically. So okay, so okay. First, let's talk about the gradient. So gradient in the notes basically is the vector that collects partial derivatives of scalar with respect to a vector. So it really is just a very special case of this general vector by vector derivative. So it's going to be, I prefer, so in numerator layout, it's always going to, gradient is going to be a column vector. So here, which one is the gradient? Yes, okay. So which of them is the gradient? There are 6 things here. Which of them is the gradient?
Scalar.
It's actually derivative of scalar by n.
Scalar by.
Yeah. So assume that this is the numerator and this is the denominator. So like this is the numerator, and you know that the gradient is going to be derivative of the scalar of a scalar function with respect to the entries in the matrix. So what's an example of a scalar function of a matrix? One example of a scalar function is the trace of a matrix. Trace of a matrix is defined as the sum of its diagonal entries. So it is going to be sigma m I, where I goes from 1 to n. I'm assuming that it's square. I'm assuming that it's square, and and that so like this is a scalar function of a matrix. You give it a matrix, and out comes a scalar. And then if you want to take the derivative of this function with respect to the entries, you can expect that there are going to be a lot of zeros. The reason there will be zeros is because Rachel.
The reason there will be a lot of zeros is why?
So if I take the derivative of this, this is going to be a matrix, right? And what I'm saying is that there are going to be a lot of zeros in that matrix. And the reason for that is,
Trace is only determined by the diagonal.
yeah. So all the off-diagonal entries are going to be 0. So and if let's say it's a vector, scalar function on a vector is just its magnitude, right? So if you have a derivative of the norm, let's say x transpose x with respect to x, this is the function which is going to be giving me a gradient. This thing is going to be a gradient because it's a scalar function, and you take derivative with respect to a vector. And so this thing, like out of all of these, you can think of them very generally. There's only this one which we call the gradient. So like one of them has a name, which is the gradient. There is another one which will have the name like this vector by vector, which we'll call Jacobian, right? And that's it. Like those are just names, but this is the general, like this is just the general thing. There is also one more note about notation, that sometimes people call the matrix the Jacobian, and sometimes they refer to its determinant by the name Jacobian. So just have to be careful which one is being referred to. All right. So now on to like more interesting things. So I would not use mixed layout. I don't know why I say. I would use numerator layout. It's just consistent. So okay, we already did the derivative of the first row, ax, which is equal to a. Can someone like tell me why this is A transpose? Or is everyone comfortable with the fact that when you take derivative of this with respect to x, the output is A transpose. Is anyone not comfortable? Not comfortable, okay. So, like, let's just use this. Oh, okay, there are markers. So when you use and then when you take derivative of this, you are basically arranging all of the partial derivatives in a particular order, and you will see that like this is going to be A11, A21, A12, A2, right? And that's why like it's A transpose. And then like I was going to introduce like one notation which can simplify, but like I don't know, like I think this is also simple and might lead to less confusion, but it's useful to know one notation when you're taking derivatives. So I'll show it for X transpose AX. So let's say you want to find, by the way, like these are all called like partial derivatives just because these are collections of partial derivatives. These are not like real differentials. And this output of this, the result of this, the fact that it is the symmetric part of A times X is important. Like just remember it because it's going to be used over and over again. The derivative of X transpose AX is the symmetric part of A into 2 into X. So one way to think of this, like when you have this scalar with respect to is that let's say that the output is some matrix D or some vector D, some row D. And I say that its elements are D1J. Now, what will be the elements, like what will be D1J? You actually think about it and you write it out. Like it takes some time, but you can actually come up with like the formula, right? So this notation is basically like this is the Einstein notation. Basically what it says is whenever the indices are repeated, you're doing summation over them, and then whenever these, so basically there are two repeated indices, so there are two levels of summation, and then when you take derivative with respect to this, because of the chain rule, this thing will split up into two different parts. Which you can then break into. So I haven't really explained this. Also, yeah, so sorry. This is wrong because this should be X transpose into A plus X transpose into A transpose. So yeah, I just want to make sure that, so in the numerator layout, when you take derivative, it's going to be X transpose A plus X transpose A transpose, right? And I mean, this is just the basic mechanics of it, this is just derivatives and stuff. And I feel feel like it's going to be very hard to explain this thing, then you just have to work it out yourself. So I'm going to skip over this and go give you like more formulas, basically. So we covered like some of the formulas. Here I'm going to cover more. So these are like in the notes as well. So imagine that both u and v are functions of x. So their derivative is not going to be 0. Like the partial derivative is not going to be 0.
Can you see the previous one, just like chain rule or something? Expression?
Yeah, this is chain. What I'm saying?
The final expression as well, x prime a plus x prime.
Yeah. Yes, you can. You can think of it as a chain rule. I'm just saying that, like, so if you think of it as a chain rule, you will have to think of it like maybe as a composition of two functions. So you're saying this is x prime, so it's like your function f is x prime
into x.
Into
Ax as one function.
Wait, sorry. Yeah, okay. Wait, how do you do that?
X prime is 1 and Ax is another.
Yeah, so first, so f is ax, and then g is x prime times f of x. Yeah.
I'm having trouble telling when in the slides you're saying prime and when you're saying transpose.
Yeah, okay, sorry. I did not mean to say prime, it's always transpose.
Okay.
It's never prime, it's always transpose. Yeah, this is also transpose. Everything, I would not use primes at all. Like, these are all transpose. Like, these are all differentials. So, yeah, I mean, you can find them out anyway. So, like, I'm going to lay out some of the important formulas, and from here you can derive pretty much everything else. So I'm going to write these more properly now. So the first one, which is important, is what is this? And here, just so by using just this formula, you can derive a lot of different ones, like change u to be some quadratic function of x, or change u to be some polynomial of x, whatever. Like it's up to you. Then this is the chain rule. And since these are non-commutative, like these are matrices, the order is important. Make sure you don't like screw up the order when you're doing the algebra. Right. So yeah, so this is the notation. And let's try to derive, let's say the last one, like why that would be. So I'm going to write this down. So first of all, like, is this sort of, is this one easy to understand, like why this should be Adrian? Yeah, I mean, like, so here's like why the chain rule works the way it does here. So, like, how is it that I was able to write this as u transpose? So, like, there's always the option of writing it, like, you convince yourself to just write it down as, in special cases, what happens. Let's say v. So first of all, let's just try to see that it's going to break down into the known cases that we already know about. Let's say V is some constant function, let's say the identity matrix, and U transpose is AX. Or let's say the U transpose is the identity matrix and B is the AX thing. Then then I am only taking the derivative of del AX and X. And if you put in these things over here, you will see that it is plus B transpose 0. So that becomes 0. So in like special cases, at least it's giving us the correct output. It's giving us the correct answer. So that's one way to convey special. But if you want to like actually derive it, like how would you go about it?
Does it have to do with the fact that each of the cells in U and V are functions of X? And since you're taking the product to like angle to each cell independently?
Yeah. So the simplest way to think of it would be, how you can apply a chain rule independently. The only thing is that, so once you apply a chain rule independently to these functions, to these things, converting it back to this form, this nice matrix form, is sort of non-trivial, and that's why we use the identities. So I think this is a simple example to do on board. So what is the derivative of the norm of a vector with respect to the vector itself? And note that here there is all this thing is coming because the norm has that square root thing. The norm is always a square root